Intellectual market. Yeah. I was doing it started. So it is my distinct pleasure today to introduce our speaker. Some of our speakers are Sacit Cetiner. I actually overlapped with him at Penn State way back. He is currently a senior research scientist at INL, but also holds a joint appointment with MIT, serving as the director of CRISP. CRISP is the center between INL and MIT, called the Center for the Advanced and Sensor Physics. Previous to that position at INL, Sacit worked as a senior R&D staff at Oak Ridge National Lab, where he led the Modern Nuclear Instrumentation and Controls Group. He earned his master's in electrical engineering and PhD in nuclear engineering from Penn State. This is where I got to know first. And in recognition of his expertise in INC instrumentation controls, he was appointed as the US DOE technical point of contact on two major projects, the BTR's experiment INC area and the TCR's sensing and controls. Maybe you're going to tell us more about these reactors in the seminar, or you can.
I'll mention a little bit.
So let's welcome the project.
Thank you very much for nice introduction. Professor Asmi actually was in my PhD thesis, so I had the distinct pleasure of knowing him at Penn State. Today, my objective is to talk about the challenges and opportunities that came with those challenges in the nuclear instrumentation and control space. Particularly for advanced reactors and those advanced reactors that are smaller in size. And also, I'm going to introduce this new center that we are establishing between INL and MIT. It's located in the Nuclear Reactor Laboratory at MIT. So you've probably seen these multiple times. These things happened in such a short period of time. We don't even, we're not even shocked anymore when we see a car driving or rockets going up and coming back down vertically, quite stably. And they've become almost norms today. It is an incredible accomplishment of technological evolution. But I would say a few things about this guy. Do you know when the first autonomous car actually was driven or drove itself? 1981 by Daimler-Benz. But it took a huge minivan loaded up with a supercomputer to be able to do the image analysis of the road. And they operated about 50 kilometers per hour in the autobahns of Germany for hours. And that computational power is now within about this big of an FPGA today. And this is what we call technological transformation. This sounds like a couple of individuals' incredible contributions, vision and contributions. Actually, governments around the world, one Bloomberg's estimate is about $20 billion to get to this point. It doesn't happen overnight, especially in regulated industries, especially in a regulated industry such as nuclear. So we're talking about autonomous control. This is the favorite topic of conversation these days, but it's going to take a lot of constant effort to get there. And for these guys, telemetry, very, very advanced sensors, and very intelligent ways of qualifying these products in space environments That's how they were able to do things in years when it took NASA for decades. So it is hard to define what autonomy means. It means self-governance. If you open it up, autonomous country or autonomous state means it is able to govern itself. But it is what we humans do, what animals do. We are autonomous. We make decisions, and so autonomous control as a language got into NASA's space in the 1970s because they were designing probes that would go to space, to Jupiter's icy moons, for example, that you cannot establish a reasonably fast communication time. I mean, forget Jupiter. NASA, the communication time takes anywhere between 20 minutes to 40 minutes, depending on the locational whereabouts of the planet. So the whole mission is, I think, 40 seconds from coming into entering atmosphere and touchdown is 40 seconds, something like that. It's by the time you inject your decision, the mission is gone by many minutes over. There's no way to introduce human into the loop. So this guy is not a fancy term. It is just, there's no other way of accomplishing it. So if you study the technical depth of how they accomplish this, so you can actually break down where the actual need takes place. It's right there. I watched this video multiple times. It's an incredible human achievement, in my opinion. And you can tell at what point the system is actually making decisions. It's, of course, there's no perfect picture of the land, and the system makes decisions, adjustments of its descent based on the analysis of the terrain. Because if you get stuck in a hole, the mission is over. Billions of dollars of investments is gone. So we need to think about when we're talking about these capabilities in nuclear systems. We need to talk about, okay, what is it that we're actually technically solving? And that question, in my opinion, is not well addressed. An example, it's if you watch this video, there's a huge scream by the staff watching this. It's the landing vision terrain relative navigation system gave a unique solution. That means the algorithm worked. So this is the kind of equivalence we need to generate for nuclear systems. So let's talk about the problem statement. What is it? What is it that we are supposed to autonomize in a complex system that's such as a nuclear power plant? It's, if you work in the nuclear control space, if you watch operators, I strongly suggest you visit the pulsar reactor. It's a boring place. It's usually don't do anything. And actually, and this is not a joke, by the way. This is an established field of human factors engineering. They actually introduce things to keep the operator's attention at a certain level, so that they don't lose connection with the system when something abnormal takes place. You can't detach human entirely from the system if you are going to rely on the human's decision making. And as you know, this is the MCAS disaster that Boeing unfortunately introduced. When the humans are not fully capable of understanding what the system's capabilities are, then you end up with very catastrophic disasters such as those the aircraft failures. So the key difference when we talk about control separating from the standard feedback control, we've been doing it since probably Tesla days. From very basic established classical controls to the controls that we are talking about. I'm not a big fan of those subjective terms, advanced or advanced, because it doesn't carry a quantitative information, but those that are beyond the standard ways of accomplishing these objectives, that actually gets into the decision-making space, which is what we humans do. So then, if we think about why we are required to have operators in the control room, and not one, at minimum two per NRC requirement. And actually, for large reactors, one senior reactor operator, one shift supervisor, and two reactor operators, one preferred senior reactor operator. That's a huge burden, by the way. There's a reason. We are not keeping those guys to keep them bored in the control room. They are just there, just in case something happens. I mean, it's no different for aircraft here, aircrafts also. They have limited job responsibilities during the flight, but when something unexpected happens, they have established heuristic rules that they automatically, and that goes back to the training, that they automatically exit, and that's what saves the day. Flight or nuclear power plant. And that even applies to, for example, Fukushima accident. I mean, it was an accident, but operators squeezed the last bit of time possible and extended the accident scenario instead of hours to days. It was an incredible success from that point of view. So operators' mental picture of the system and understanding the phenomena involved is very important. So that goes to the decision-making capabilities. And that's what we're talking about. And when things are steady state, there is no decision. It just doesn't make sense. These kinds of more cognitive abilities that require some cognitive ability or actions that require cognitive abilities, they start to make sense when you're talking about major operations. When do these happen? Mode transitions. It's another fancy word from going from one power level to certain power. You're at cold standby, you're going to hot standby. Hot standby to low power to mid power to ramp up to full power, and these are modes and mode transitions. Or you can have unexpected transients. So this whole thing is what operators do is to make sure that the system is safe, stays safe, and if possible, steer it back to a stable condition or at least an acceptable condition. So this is my personal opinion. We are talking about the necessity or a requirement for significant reduction of human staffing in these reactors is not only because they're financially creating undue burden on these systems, but also if these reactors are to operate in more frequent, almost transactional manner, meaning with the grid, they constantly exchange information about, okay, this is the load level I'm going to get to in 1 hour. That these high duty cycles will inevitably lead to faster component degradation. And that's where the critically important lays. We do that, the Navy does that, has been doing that for many, many years, but Navy can replace any component without a failure. And even that is very costly, but to keep these systems at minimal operational and maintenance costs, we have to work on optimizing that aspect. And the challenge, because it is a complex, you have systems, components interacting with each other in many combinatorial fashion, and it becomes an untractable explosion of states. And because of these hard to model uncertainties associated with each component, we need to bring in this sequential decision-making capabilities. And then, in my opinion, this is the technical explanation of what we should be calling autonomous or semi-autonomous control capabilities. And this is important. This is coming for, especially for smaller reactors, the micro reactors, those that have a few megawatt to 10 megawatt output. Its calculations show that if you have more than 5 FTE to one person, it's already too expensive. That's beyond that becomes a significant burden on the financial viability of these, economic viability of these systems. So what are we talking about? It is the INC system. It's been an intricate part, an integral part of our safety philosophy from the very beginning. When I worked at Oak Ridge National Laboratory, I visited the graphite reactor many times, and I had the pleasure of taking a tour from a very knowledgeable expert. And it goes back to our separation of protection, the safety and non-safety control functions. That philosophy goes back to the early days of the establishment of these reactors. Even goes back to the Chicago fire. So we are. This hasn't changed. It's codified in our sort of federal regulations, in our standards. This is how we've been doing these implementations. And the whole idea is that you assign certain functions of importance or safety significance to reactor protection system, such that in the event those set points are violated, the RPS automatically initiates the what we call scram function, which is the fancy word for shutting down the reactor. And then you have the means to display the critical parameters, minimum inventory display, and then alternative ways to manually shut down the reactor. And then you have the reactor control system. That's how we operate the reactors. This is across the board. This is how we engineer these systems. This is how we design these systems. But this is proving to be an extremely costly approach, and probably we're going to need some rethinking as to how we can accomplish these functions without compromising on the safety in different ways. So if you look at the list of instrumentation in a nuclear power plant, it's no different than any major thermal plant. It's the only distinction being, of course, the monitoring of neutron population at a given time, and of course associated heat, thermal related performance, temperatures, pressures, flow rates, and if it's applicable, such as BWRs, it's the level. The process has also gotten to a point where bringing in something new became almost an impossible. So my colleagues and I were working on a journal article, and I happened to be leading the cost model on instrumentation control. So I reached out to companies on just to get some understanding on, okay, what is the landscape for example, temperatures, safety grade temperature sensor. It's incredible. It's a single thermocouple. Takes about $50,000 to $100,000 to buy for that one parameter. And for one parameter, for one variable, you need 4 of them for 3 out of 4 redundancy. And it's to use that for controls purposes, you need input and output, of course, to generate the delta T information. 8 temperature sensors right there. It's a major cost item. And it is not because these are incredibly different than technology-wise and then things you buy from Omega, for example, for $50, but it's the process and the traceability of the documentation and the fabrication processes that are involved. It applies to everything, pressure, flow rate, and it is a huge burden on the industry. And it's not only that, it's when we talk about anything safety, then we're getting into the space where you have to have surveillance, periodic surveillance, inspection of these components, channel testing, things like that. It's costing a lot of maintenance time on these systems. So it is, in my opinion, we need to come up with somewhat different, non-traditional approaches to this. We will not saying that we're not going to have anything safety related, but we need to really think about how we should classify these systems in a more risk-informed manner that will not require the same level of investment. And when you get to what's called advanced reactors, and this is NuScale is semi-advanced reactor, it is basically a boiling water. But now that the approach, the philosophy is to do away with potential accident paths. We eliminated all the lower penetrations or the side penetrations to minimize any probability of loss of coolant accidents. Then the only accessible space for critical instrumentation to be able to incorporate it into the core is the reactor top vessel. That means your instrumentation stall has to come all the way from the top of the reactor and then get into these critical places. And it's, I know from NuScale that's been one of the challenging problems that they attacked from the very beginning. Their approach was very solid from the beginning, and I very impressed with their approach. Not only the sensors and instrumentation, but also INC in general. For example, they were able to show to NRC that they did not need any emergency diesel for powering these critical devices, and it was accepted. So we're having these conversations, but we are also running in circles. There's just not enough investment in this space, which slows down or which impedes the technological advances coming into the mainstream, as opposed to the example that I gave in the automotive space that proliferated very quickly. And it's been a major hurdle in these technologies. When we were building these reactors in the 70s and 80s, almost all reactor developers they had dedicated instrumentation control divisions that were entirely on developing new instrumentation or improving the performance of these instruments. This is an example from 1985. They DOE under the liquid metal reactor program, the advanced liquid metal reactor program, they established a center called ACT, Advanced Control Tech Operation Program. And it's very interesting. This is the core statement from that from this article, and it is the vision and objectives are no different than what we are trying to achieve, what we are trying to accomplish in our center. Become a central resource for tackling these challenging problems for the nuclear industry. It's 1985, we're almost 2025, it's 40 years, we're going in circles. And to me, I think that this is unfortunate. And also, around the time I graduated, there was a renewed interest by the NRC on establishing this guide, a central hub for instrumentation control research, but focusing mostly on digital INC. At that time, the industry was having a hard time convincing getting NRC approval for getting the license evaluations of digital INC upgrades or for new reactors digital INC installations. So that one focused mostly on that aspect. But again, the conversation was visited again. It's to establish a common capability, common resource. I want to give an example. I think from the 1980s. In the 1970s, a number of reactors had loose parts issues that led to flow blockages, and the NRC issued a SECI paper, and then asked the staff to look into establish a program for identifying potential loose parts in reactor systems. It's a very great application of how do you sense stuff, how do you interpret data, and it's a fancy term of data analytics today. That was done at that time, and the industry came together, and under the leadership of EPRI, they developed this regulatory guideline to codify how we can monitor these loose parts that may have been introduced into these systems. And now it's codified into ASME O&M standard, and everybody does it. It is these standardizations are a great way to reduce costs and improve plant availability. And today, this is the standard practice. I'm using these examples, and I think this, in my opinion, a great success story provides an understanding or sheds light on an understanding that a similar approach is needed if we are to push these reactors, especially next generation of reactors, into more financially viable, economically competitive mode in these markets. I don't think the problem is today's market. It's the market pressure will exist. We have to optimize system end to end, not only the fuel management, not only this and that. It's entire. You build a reactor in 5 years, design in 5 years, build in 5 years, but you operate it for 30 years, 40 years, and we have systems going to 60-year and 80-year life extension. So the operations and maintenance is an important part of this process. So that is the fundamental raison d'etre, the reason of existence of Center for Reactor Instrumentation and Sensor Physics. We wanted to call it sensor physics because I am of the opinion that there are transduction modalities that have not been explored, because when RICO wanted these reactors built for the Navy, you just couldn't wait on a new instrument development. So they relied on things that existed on the shelf, and then they called it the process qualification. And it just hasn't changed. And if you look at other application areas, like space programs and others, there's really advanced instrumentation, such as electromechanical devices, that show great promise, even under very harsh conditions. And I think there are opportunities to improve in that space. And broadly, we break down this end-to-end measurement loop. You measure something, you process data, and then you take a control action. And I think these are the three distinct boundaries that we can find. And if we are to attack this problem, we have to attack the problem on all fronts. And that's where Chris comes in. When I was approached for this position, I was very excited for the center being established at MIT, not because MIT being, of course, a premier education institution, but also with a lot of established sister institutions, organizations, such as Lincoln Lab, Draper Lab, and they're already developing these advanced concepts, bringing these advanced concepts of sensing, or in the case of, for example, robot automation, in other application spaces. I think the cross-pollination and getting that information transferred over to our space is a more efficient way of accomplishing our objectives. So it is jointly funded by INL and MIT. It's not under any program, and it is, of course, connections to INL's organizations, many programs that I interact with. I'm interacting with relevant departments. We are looking into potential interactions within NRIC to test, potentially test the INC system for customers. And DICE is another center that was established a couple of years ago. It's looking at the digital problem from a digital engineering point of view, and going to the whole civil construction process. And on the MIT side, as I mentioned, of course, there are centers, there are sister labs that have significantly established capabilities and departments. So we are still new. I have faculty affiliation from the Nuclear Science and Engineering Department, of course. Many of my colleagues, we are working together, writing proposals, discussing ideas, but there's also faculty involved from other departments and mechanical engineering, for example, electrical engineering. I have a couple of additions after this slide, and it's those interactions are helping bring some of the capabilities that already exist in other departments to our field. Right now, 2 PhD students working with me. Haesung is working on spark sensing area, and he's a graduate fellow at INL. And Jen is working with on quantum sensing with a faculty member. So I want to talk a little bit about facilities and capabilities. Of course, in establishing a new center, our objective is, or vision is to pull industry into this new idea, this new organization. And to accomplish that, we need to have we need to be able to offer return on investment on their time and on their investments, obviously. And of course, having the MIT reactor on site, it provides some opportunities for example, instrumentation testing or material testing for new instrumentation development. This is one of the ongoing project that recently started, that awarded and started this year, establishing a second water loop capability in the MITR. And it offers opportunities for testing potential new instrumentation materials in representative environments for PWI and BWI conditions. This is a facility that I'm very excited about. MITR has an interesting structure. So it's a black water moderated core, cooled and moderated. It's surrounded by DTO for reflection, and then surrounded by a block of graphite. And within that graphite, we have 6 positions available that come down at a slightly slight tilt right next to the reactor core. And the advantage of these positions is they provide large openings, about 3-inch diameter openings to accomplish to be able to perform large equipment irradiation, such as not only a material for a sensor, for example. We have, for example, interest in some customers for radiating full instrumentation package or hardware that goes into that. So we are able to replicate the some of the conditions that they're such as dose rates and total integrated dose in these conditions by using flux boosters in this facility. So that's one of the projects that we are looking into, how the fast flux, at what level we can boost it to. Our calculations show that we can easily get to a few order of magnitude boosting. Still not major research vehicle for material fuels irradiation, but it is a major fast flux level for instrumentation purposes. Another interesting ongoing project is that North Carolina State is also involved is the installation, the design and installation of the molten salt loop, and it goes into next to what's called the ATU booster fuel that is neutronically decoupled from the reactor, providing somewhat large fast flux level. And this is where the loop will be installed, and I expect it will provide opportunities for instrumentation testing for these environments, particularly salt, which is hard to find in the irradiated flowing capability. So far, I discussed the center and things at a high level. But I want to get into a couple of examples about what we had done. I was personally involved in some of the research that we did under the versatile test reactor program or the transformational challenge reactor program. So just very briefly, versatile test reactor was this fast spectrum liquid metal sodium cooled reactor that DOE was planning to build and then changed mind. Unfortunately, it was canceled about a year ago, and we don't know if it will have a future. But the objective was to provide significant fast flux irradiation capabilities, materials and fuel testing capabilities in the United States, which currently doesn't exist. Many of our advanced reactor vendors that require data, they go to Russia or China, and not those facilities are not always easily accessible, and these resources are not easily useful. So that was the objective of the versatile test reactor. And the transformational challenge reactor was a smaller reactor. It's a megawatt reactor, but there was a unique aspect to that. It was the core was to be, I think, the core structures, and the fuel was to be 3D printed, additively manufactured. It was going through the qualification process in the MITR. That project was unfortunately unplugged. So some of the examples that I will share with you in the somewhat advanced sensor space, there are a collection of some examples from the activities that I was involved. So flow measurement is a somewhat mature technology even for sodium cooled reactors. But these reactors, because they involved different testing of fuel assemblies, fuel test assemblies, or driver test assemblies, or material test assemblies, their internal configuration changed from cycle to cycle. So characterizing the flow conditions in these reactors at the assembly level was understood to be an important information. So the fast flux test facility, for example, had I think 12 of the instruments in the driver assembly and reflector assembly positions. It's called eddy current flow meter because it implies creating eddy currents by one solenoid, and you hit it with an AC current, and then the eddy currents induced by those primary magnetic fields, they induce secondary currents in the subsequent secondary coils, and it acts like a linear variable differential transformer. The advantage that particular instrument brought was very high sensitivity and very small form factor, literally almost pencil size, and another advantage being there's not much for radiation to damage it. It is literally just a couple of coils. As long as you have the proper insulation that will survive in the core environment, they perform greatly. So that was identified to be a technical gap. Even though it was done for the FFTF, the documentation was long lost, and we identified this as an area that we needed to work on. And in the VTR experiment area, two of our cartridge loop customers, those are experiment designers going into the experiment position in the VTR. Two of them were liquid metal reactors. One lead, the other one was sodium, and both needed to measure the flow rate for balance calculation purposes. So it had somewhat safety significance. This is how it looks like. These are the ones that went into FFTF. So we built test facilities. We built these loops. First of all, we designed a detailed multiphysics model that captured the flow and coupled to the electromagnetic, electrohydrodynamic calculations, and then validated our models. Everything from equation state to these the electromagnetic induction, and as well as the final signal generation. And this was the measurements were done at the ORNL SNS Mercury Loop facility. This is the exact replica of the ORNL installation neutron source facility. You can see this is a huge facility. This is the guy you're looking at in this picture. So it's a very big mercury flowing facility. So we were able to validate our models, our multiphysics models at room temperature, and show that there's confidence in using these models to build high temperature applications of these sensors, because fabricating this sensor is cheap, but when you're doing it for high temperature applications, it becomes very expensive very quickly. This is a sensing idea that we came up with for the transformational challenge reactor, which is an NAPGR, basically, really cool reactor. And we asked the question, would it be possible to come up with a whistling passive system that conforms to that meets this requirement? It radiates acoustic emissions with frequencies proportional to gas flow velocity. The idea was not to replace a standard conventional flow meter, but would it be possible to identify flow conditions in individual channels. And so we asked the subsequent questions, and then we realized that there's actually a possibility. And actually, there's a published detailed literature on this topic called corrugated pipes, which is an annoyance in industry. And by going back to the basics of periodic structure and solving these boundary conditions for the interaction of acoustic waves with the gas flow, we were able to come up with a design of periodic structure, and refining the small features of these structures. We were able to generate a quite linear behavior, starting from started from LES, and we were able to demonstrate that we can go to URAMs and still meet our quality of computation, and then show that this is the experimental result, by the way. By changing the flow rate, this is with air, you can actually get a very good idea about what the flow velocity is. And this is of course showing some nonlinearities, but by tuning the surface features, these corrugated structure features, you can linearize it and generate quite an interesting acoustic response. And it doesn't require any connection to power source, doesn't require any signal connection. You have these passive structures within the core, and then you just through a high dynamic range microphone, you can actually you're creating a spectrogram that shows how the flow is changing. And again, by fine-tuning these structures, you can have one channel resonating at one frequency, and another channel resonating another frequency. So it gives you a way to discriminate between flow channels. And we're actually we were able to secure a patent from that, and we're looking for licensing opportunities for that. It may have applications in other areas as well. This is an area that I was directly involved technically. Ultrasonic thermometry has been around since I think the original concept goes to 1960s, if I'm not mistaken. But usually you launch a wave, and then you have some reflection points, and you look at the reflected spectrum, and from the time of flight you determine the local temperature between the sensing points. But what we did was again introducing periodic structures in different forms, either through surface changes, geometric changes, or by introducing different material, essentially creating what's called an alternating acoustic impedance structure, similar to optical phononic structures like Bragg gratings. We were able to control the wave propagation very accurately. And here we fabricated one with aluminum and copper using ultrasonic additive manufacturing, and this was additive manufacturing at the Orinal facility, just metal printing facility. Just want to quickly just to give you an idea about how it works. So you want to interrogate this guy, you want to know what's going on there, but you don't want to lose your signal here, because every time you cross a boundary, you'll lose a fraction of your energy. And it's almost, you lose some, but if you design it well, you can minimize the loss of energy you can keep the loss of energy to a minimum. So that was also another, we were able to secure another patent out of that. And it's, we show that it's, when you do either experimental measurements or low order, one-dimensional elastic wave propagation calculation, or 2D exact calculations, they met well. They were quite in good agreement. So this is an area that I am gravitating towards. It's an emerging area called metamaterials and meta surfaces now, with very precise either lithography capabilities or direct 3D printing capabilities. It is possible to create very intricate surface functionalities that lead to interesting behavior, just like the one I mentioned with the acoustic emission flow meter. By looking at the surface reflectance and transmittance spectrum, you can interrogate, you can identify certain things, temperature or strain conditions on that surface with no electrical or signal connection. Interesting research areas, and this has been studied in the optics domain for years and years, and there's more and more publications coming out in the sensing domain, and there may be applications for nuclear and process monitoring. So this is the end of the presentation, and I'll be happy to entertain your questions.
First, the people who are online, if you want to send your questions by on the chat, or speak up, unmute and speak up if you can. I'm going to stop sharing. Please talk now.
Yeah, your flux booster. I thought that was novel. I really like that. One of the issues that would come with that is that you would want to get as close to the core as possible to have your flux be high, but by getting closer to the core with that high flux, you're going to start heating. And at some point, you're going to start threatening the heating environment. And there's going to be some kind of a play there. So some kind of like a maximum thickness that you can get when you're up there next to the core. How did that work out for you? What was the process result?
Just with full disclosure, that facility was, I think, designed and built in the 80s for boron neutron capture therapy purposes. So I don't know the specifications in detail, but through I'm sure many iterations, they were able to find the right sauce for thicknesses and proximity to the reactor core. But the reason I think we're able to pull it off is because the reactor, through many shielding barriers, is neutronically highly decoupled from what's happening in the reactor. So it doesn't impact reactor operations. You can when you open the shutter, it doesn't impact any measurement on nuclear instrumentation. And I'm sure there are there are many detailed analysis that went into that, but that system was it didn't even require licensing, if I'm not mistaken, because they were able to demonstrate the decoupling. Of course, there's cooling requirements, there is retention of fission product and all of that, but based on what I was told, it is maybe it was licensed in the original plant when the plant underwent a modification in 1970s, and then I think it is within the jurisdiction of the Safeguards Committee, but I'm not. I shouldn't be answering this question. Okay.
Any other questions?
For the microreactors, tuning with will get at some point will remove the safety aspect and control. So we can work more monitoring one. So we gave the operators out completely, we're still gonna make it for calibration. In terms of the next generation of instrumentation and control, where do you see it? Where do you see the biggest gains?
I think it's going to be the operation that means.
Do you envision the microreactor being transferred to the back factory for calibration or still sending people on the site?
There is, I think there are a lot of open questions. How do you transfer, even transport of an unused core is challenged because maintaining the subcriticality during the entire transport and making sure that nothing can violate that. I think that alone is an unanswered question, but especially for a core that has significant burnout. I don't know what the requirement will be, but I am of the opinion that the online monitoring and the incorporation of maintenance strategies into the formal maintenance plan that plants have to submit. I think that's going to be the biggest gain in terms of return on investment. It's gonna take some time.
What is going to be, because we already have maintenance plans.
We have predictive plans based on prescribed vendor driver data. But the second, and especially I think that's going to be more true for reactors that operate in the low quality mode. We will see more and more of these equipment wear outs, and those need to be those will have to be addressed. And will we somehow decouple the primary system from the load changes through some kind of thermal isolation to be seen, like thermal battery in between to be seen, but it will be more ubiquitous, broader penetration of instrumentation at the component level, so we can collect. It's in my opinion, it is no different than the kind of sense of pain in our bodies. It gives us preliminary information about something non-conforming, and it's an early warning sign, and then we go take action on that. I think that is the analogy that I see. Once these more deeper penetration of sensors and potentially embedded directly into the components, we will be able to get direct data instead of inferential data, and that will eventually inform the maintenance practice. There are a lot of unanswered technical questions. How do you connect a certain signal to potential failure mode? It is these are complex problems.
There's a question here. Do you believe that the current methods can be seen here? Oh, you can see it here. Okay. I was going to read it, but now that everybody can read it.
Probably not. I mean, our plants, the current plants, they were uniquely built, and I don't think it is the transfer option. I don't think that's a possibility. But if you have standardized deployment of units, for example, new scale, you have 6-pack or 12-pack, that information will be translatable to other units.
Okay, if there are no more questions. Let's thank Sacit one more time. uh,